All right, so let's start. So in this lecture and in the next lecture, I'm going to solve some of the classwork problem for chapter 16. All right, so let's start with this one, the first one. It acts as to find the magnitude and direction of the electric force. Okay, so the given stuff here are the charge. Okay, so the charges here are the proton, okay, and the electron of a hydrogen atom. Okay, so you know that hydrogen atom has a proton and an electron. Okay, so proton is inside the nucleus and electron is in the outer shell. Okay, and if you remember from the lecture, the radius of an atom approximately is 10 to the power minus 10 meter. Okay, so for this one, let's use the radius or the distance between the proton and the electron is this. Okay, so we are given the charges, we are given the separation between the two charges. We have to calculate the force, okay, the magnitude and the direction of the electric force. Okay, now you already know what is the equation, right? The Coulomb force is F equal to K Q1 Q2 over R square. So K is the Coulomb constant, and the value of Coulomb constant is this 9 times 10 to the power 9 Newton meter square Coulomb square. Okay, now the charge of electron and charge of proton both are the same, and the value is this 1.6 times 10 to the power minus 19 Coulomb. Okay, and the same thing for proton. Okay, right, don't use the sign. So normally we use plus E for proton, minus E for electron, but here when you calculate the magnitude, don't use the sign. Okay, this sign. Okay, use all positive, I mean the absolute value of the charge, and that is this. And the radius between, or the separation between the proton and electron, here you already see that this distance r. Okay, so r is given this 0.53 times 10 to the power minus 10 meter, and this is square. Right, now if you plug all these values in your calculator, it should give you something like this. I got 8.2 times 10 to the power minus 8, and this is force, so it is Newton. The unit is Newton. Okay, all right, so this is the magnitude. Now still we have to calculate, we have to determine the direction. Okay, so we have to determine the direction of the force on the electron. Okay, so it says that determine the magnitude and direction of the electric force on the electron, okay, by the proton. Okay, so here is the proton. Proton has positive charge and electron has negative charge. Okay, now if we have a positive charge and if we have a negative charge here, normally you know that positive and negative are attracted by each other. So in this situation, if there is just a single positive charge and single negative charge, positive charge will feel an attraction in this direction and negative charge will feel an attraction in this direction. Okay, now because we are asked to determine the direction of the force on the electron, so our direction will be this one. Okay, to the left. So this is our answer. Okay, all right. the next one. Okay, so here we are given again 2-point charges. So one is this one. So again we are given 2-point charges. One is this, okay, another is this. Okay, 2-point charges, and they are separated by a distance L, although there is no numerical value of L. And it asks us to find what is the larger in magnitude, the force that Q1 on Q2 or Q2 on Q1. Okay, you probably already know the answer, right? So the force Q1 exert on Q2 and Q2 exert on Q1, both are these. Okay, so if I write F1 for for the force on Q1, it will be K Q1 Q2 R, L square, and the force on F2 will also be the same magnitude. Okay, so the answer is the magnitude will be the same, although the direction will be the different. Okay, direction depends on the depends on the sign, right? Whether they are positive or negative charges. So because both are positive charge, okay, the direction will be, one will go in this direction, another will go in this direction. Although the directions are the different, the magnitude will be the same. So the answer is the magnitude is same. Okay, next question. Now we have 3 charged particles. Okay, so you see that here on the left we have a negative charge, and in the middle we have positive charge, and the negative charge on the right. Okay, now we have to calculate the net electrostatic force on particle 3. Okay, so you have to calculate this, that means on this charge. Okay, due to the other 2 charges. Okay, so we have to calculate the electrostatic force, net electrostatic force on Q3. Okay, calculate the net electrostatic force on particle 3. All right, due to the other 2 charges. Okay, so if you remember, so when I talk about the superposition, okay, so if we have some situation something like this, we have to individually determine the force. Okay, so for example, in this case I have to first calculate the force F3 by 1 and then F3 by 2. Okay, and then we have to check which one, check the direction. Okay, so basically we have to use the vector rule. Okay, so first let's calculate F31 and F32, and then let's try to determine their direction, and then we can decide how to use the vector rule. Okay, all right, so the first one is F31. So F31 means the force on 3 by charge Q1. So it will be K Q3 Q1 and then R13 square. Okay, so K is 9 times 10 to the power 9 Newton meter square Coulomb square. Q3, okay, Q3 is 4 microcoulomb. So micro means 10 to the power minus 6 coulomb. Okay, although it is negative charge, okay, don't use the negative sign when you determine the when you calculate the magnitude. Okay, so don't use the negative sign. And Q1 is also negative, but again don't use the negative sign. And micro means 10 to the power minus 6. Okay, and R13 is 0.3 meters, so this plus this, right? So it will be 0.50 meter, and don't forget to square it. Okay, so this is equal to, so I already did it, and I got something like this: 1.20 Newton. Okay, now let's calculate 3 by 2. Okay, so same equation, I mean similar equation, Q3 Q2 R 23 square. Okay, so again it is 9 times 10 to the power 9 Newton meter square Coulomb square. Q3 is again 4 times 10 to the power minus 6 Coulomb. Q2 is 3 microcoulomb, means 3 times 10 to the power minus 6 Coulomb. And the separation between Q2 and Q3 is 0.2. Okay, so 0.20 meter square. Okay, now I already calculated what it is, and it is 2.7 Newton. Okay, so you see that we determine the individual forces that acts on Q3. Okay, now we have to understand what is the direction of these individual forces. Okay, so to do that, so think about, just you have Q3 and Q1. So Q3 is, sorry, Q1. Okay, this is Q1 and this is Q3. Both are negative. Okay, so as you know that like charges repel each other, so the direction of F31 will be this, right? I mean, because both are negative, it Q1 will go in this direction, Q3 will go in this direction, but we are interested on the force on Q3. Okay, so the direction of Q3 will be this one. Okay, now similarly, Q2 is positive and Q3 is negative. Okay, so the direction in this case, because they are opposite charges, they will attract each other. Okay, so the direction of 3,2 will be this one. Okay, so in our usual convention, right, so if we use our x-axis, right, so x-axis means right is positive, right, the left is negative, right, and you see that F32 is to the left. To the left means negative, so the net force will be negative 2.7 Newton plus positive 1.2 Newton. So it will be negative 1.5 Newton. And that tells us that the net force, the direction of the net force will be in this direction, to the left. Okay. So you see that it's a concept. Okay, so if you don't understand the Coulomb's law and how the positive and negative works, it will be difficult to do this kind of problem. But if you understand that concept, it's not too difficult. Okay, so let me know if you have any question on this. There may be a question in the midterm exam, very similar. Okay, so yeah, make sure you understand this kind of problem. All right, the next problem is this one. Okay, so it's again a little bit complicated than the last one. Okay, but if you understand how to add vectors, okay, again it is not too difficult. Okay, so what we are given here, we are given 3 charges and the separation in this picture, and we have to calculate the net force. Okay, and the net force we have to calculate is on the charge Q3. Okay, so what is the Q3? Q3 is this one. Okay, All right. So what you have to do, we have to first determine the individual force, and then we can add them using the vector rule. Okay, so let's try. Uh, so first let's calculate F3 by 1. Okay, so it will be K Q3 Q1 and then R31 square. So K is 9 times 10 to the power 9 Newton meter square Coulomb square. Q3 is 65 microcoulomb. 65 microcoulomb means minus 6 coulomb. And what is Q1? Q1 means 86 microcoulomb. Okay, micro means 10 to the power minus 6. And the separation between Q3 and Q1 is this separation from here to here. And you see this is 60 centimeter. Okay, 60 centimeter means 60 times 10 to the power minus 2 meter. And then we have to square it. Don't forget the square. Many students forget this. Okay. And then if you plug all these values in your calculator, it will give you this. I got 140 Newton. Okay. Similarly, we can calculate F32. Okay, F32 will be this K3, Q3, Q2, and R32 square. Okay, again, K is 9 times 10 to the power 9 Newton meter square Coulomb square. Q3 is 65 microcoulomb. Okay, and Q2 is 50 microcoulomb. Okay, and then the separation between Q3 and Q2 is this one, 30 centimeters. So 30 times 10 to the power minus 2 meter and then square. Okay, so you have to plug these values in your calculator, and I got something like this when I plug these numbers in my calculator. 325 Newton. Okay, now the next step is a little bit complicated. Okay, now we have to use the vector rule. Okay, because here you will see that the direction is not along the x-axis only. Okay, so we have to use the analytical method. Okay, so here you see that Q3 is positive. Okay, and Q1 is negative. Okay, so there will be attractive force. Okay, so the direction of okay, so let me make it a little clear. Okay, so the direction of F31 will be the sorry, okay, will be this one. Okay, so this is positive, Q1 is negative, so the force will be attractive. So Q3 basically go towards Q1. Okay, so the force on Q3 by Q1 will be this one. Okay, all right, so this is one force F31, and then Q3 and Q2 both are positive, right? So positive forces, positive charges repel each other. Okay, so the direction for this one will be this. Okay, so F32 will be upward, right? Because it is repelled by Q2. Okay, so what we see here, let me erase. Okay, so if I just draw the forces, it will be something like this. So let's say we have this coordinate system. Okay, so we see that 3, 1 is this and 3, 2 is this, right? So if it is X, if it is Y, so our F3, 2 is this one, and F31 is this one, right? Now you see that 3 2 is easy because this is along the y-axis, okay? But then we have to know what is this angle, okay? Now I mean, you have to break this vector F31, and to break this vector you need to understand what is this angle, okay? Now how to calculate, how to determine this angle? Okay, you can determine this angle by knowing the by knowing that this is 30 degrees, so it's already given. This is 30 degree, this is 90 degree. So if it is 90 degree and if it is 30 degree, this angle will be 180, right, minus 90 degree minus 30 degree, right? So it will be 60 degree, right? Now this is our in our coordinate system, this is our x-axis, right? So if it is 60 degree, this will be 30 degree, okay? So think about it. So this is 30 degree. So now we know this is 30 degree, right? So now we have all the information, okay? So what you have to do, we have to follow the vector rule, okay? All right. So now let me break graphically F31. So I draw a vector, I draw a line, okay, from the tip of the F31 to the x-axis. So because this is parallel to the y-axis, this is my y component, and then this will be my x component for F31, okay? All right, so F31x will be F31 cosine 30 degree, okay? So if you plug the value F31 cosine 30 degree, okay, so F31 is 140 Newton, and then cosine 30 degree, and that is equal to 121 Newton. Okay, similarly, F31y will be F31 sine 30 degree. But make sure you use a negative sign because you see that F31 is downward. Okay, so again, 140 Newton sine 30 degree, that will be negative 70 Newton. Okay, negative 70 Newton. Very good. Now F32x equal to 0 because there is no component along the x-axis for F32, and F32y will be 325 Newton. All right. So for the net force, we have to add the x component together. So Fx will be F31x plus F32x, and that is equal to 121 Newton. And then Fy will be F31y plus F32y. Okay, and here F31 is minus 70 Newton and 325 Newton, and that is equal to 255 Newton. Okay. Now what is the net force? Net force is F equal to square root of Fx square plus Fy square. So 121 Newton square plus 255 Newton square. Okay, and that is equal to 282 Newton. And what is the angle? Angle theta is tan inverse Fy divided by Fx. So tan inverse, here Fy is 255 Newton, and Fx is 121 Newton. And if you plug this value in your calculator, it should give you this 64.6 degree. So the angle is 64.6 degree. Okay, and what it means? It means the force's direction will be somewhere here. Okay, so this angle will be 64.4 degree, and this is the net force. Okay, and in this figure, it will be somewhere here. Okay, so yeah, so please go through it, and if you have a question, let me know. Okay, it's a little bit you probably need a little bit of time to understand. Okay, all right, next is number 5. Okay, okay, so calculate the magnitude and direction of the electric field at a point P, which is okay, so we have to calculate the magnitude and the direction of the electric field. So this time it is the electric field at point P, okay, which is 30 centimeter at point P, which is 30 centimeter to the right of a point charge. Okay, so we have a point. So we have this point charge. Okay, all right. So if I draw the situation, it's something like this. So we have a charge Q, okay, and whose magnitude is -3 microcoulomb, and it asks us to calculate the magnitude and the direction of the electric field somewhere here. Okay, that is 30 centimeters. Okay, so this is a negative charge. Now the definition of the electric field for a point charge was this: K Q R square. Okay, so again, just plug the values. And Q here is 3 microcoulomb. Okay, and R square is 30 times 10 to the power -2 meter, and then square. So this gives me 3 times 10 to the power 5 Newton per coulomb. So yeah, Newton per coulomb is the unit for the electric field. So this is the magnitude. Okay, so again, don't plug the negative sign here. Okay, so we don't need to plug the negative sign when we calculate the magnitude. Okay, but then for the direction, so now let's try for the direction. So we have a negative charge here. Okay, and you know that for the negative charge, the direction of the electric field is towards it, right? So remember in lecture we did this kind of thing, right? So for negative charge, the direction of the electric field lines are toward the negative charge. So in our case, then it will be to the left. Okay, so because our this is our point P, this is our negative charge. Okay, so the direction of the electric field at this point will be to the left. Okay, all right. All right, so here the next problem again, we have to calculate the direction and the magnitude of the electric field at a point P. Okay, so P is here, and then we are given two charges on the two other side. Okay, so one is this one, Okay, so one is this one, another is this. Okay, so let me just use this. So one is this one and another is this one. Okay, and we have to calculate the direction and magnitude of the electric field at point P. Okay, and also we are given that Q1 is 2 centimeter from point P, and Q2 is 10 centimeter point, point P. Okay, so first one, we have to calculate the direction and magnitude of the electric field. And then he said that if an electron whose mass is this is placed at rest at point P and then released, what will be its initial acceleration? So here we have to calculate both the direction and the magnitude of the acceleration. Okay. Okay, so first let's try to calculate the electric field. Okay, so similar to the electric force, when we have multiple um, forces in multiple charges, then we have to individually determine the electric field. Okay, so when we calculate the electric field, remember that we need only one charge. Okay, so many students here make mistake, they just calculate the force, okay, between Q1 and Q2. Okay, remember that here we are not interested on force, we are interested on electric field, and to calculate the electric field we need only one charge. You know that the definition of the electric field is this: E equal to K Q R square. Okay, so because this is the electric field's um, definition, we need only one charge. Okay, so for example, um, E1, okay, E1 will be uh, the electric field for Q1. Okay, so for E1, I write K, the constant, Q1 and R1. Okay, and R1 is 2 centimeter. Here you see this is the 2 centimeter, and similarly R2 will be 8 centimeter. Okay, so make sure you understand this. It's the electric field, not the electric force. Okay, for electric force we need two charges. For electric field we need only one charge. Okay, now let's plug the values. And Q1 is 25 microcoulomb. Okay, and R1 is 2 centimeter. Centimeter, always we need to convert it into meter. Okay, so this is the magnitude. So if you plug these values in your calculator, it should give you something like this: 5.6 times 10 to the power 8 Newton per coulomb. Okay, similarly E2 is K Q2 R2 square. Okay, so it is 9 times 10 to the power 9 Newton meter square per coulomb square. And then this 50 microcoulomb, and then this is 8 times 10 to the power minus 2 meter and square. Okay, now plug these values in your calculator and it should give you something like this. Okay, so these are the magnitudes, E1 and E2. Now you have to understand what are the direction. Okay, so now you see that Q1 is negative. Okay, and for a negative charge, the electric field direction is towards it, right? So the direction will be in this direction for E1, right? And for Q2, the direction is always outward, right? So it will be in this direction. Okay, it will be in this direction. So because we are only interested on the at the point P, so we just need to draw these two lines. Okay, so one is for E1 and another is for E2. Okay, so this you can also determine by placing a positive test charge here. Okay, so if you place a positive test charge here, in which direction it will move? Okay, so for example, if I put a positive test charge, it will move in this direction. Right, so if you put a positive test charge here, q0, q0 will move in this direction. Okay, for q for the negative charge, and for the positive charge it will also move in this direction. Right, for q2 it will also move in this direction because q0 is a positive charge. Right, for q2 it will move to the left, and for q1 it is also moved to the left. Okay, so now you can determine the direction in two different way. One is by knowing the electric field line for for a positive or negative charge. Okay, and the second one is placing a test charge here at point P, and then determine individually how it travel. Okay, so yeah, let me do it again to make it clear. Okay, and let me use another color. So if you put a positive test charge here, okay, this will move because q1 is negative and q0 is positive. Okay, so it will move in this direction for q1. So the direction of e1 is this. Now compare it with q2. Now because q2 and q0 both are positive, q0 will also move in this direction for q2. So both e1 and e2 are to the left. Okay, so the net electric field will be negative 5.6 times 10 to the power 8 Newton per Coulomb, and again it is negative 0.70 times 10 to the power 8 Newton per Coulomb. Okay, so negative 6.3 times 10 to the power 8 Newton per Coulomb. Okay, and this negative sign tells us that the direction is to the left. The net electric field's direction is to the left. Okay, all right. So it's very similar. This problem is very similar to this problem. So here in question 4, we determine the force, net electric force, and now for this one we are going to calculate the electric field. Okay, net electric field. Okay, at the same it's basically the same thing. Okay, all right, so let's try to determine. Okay, all right. So first let's try to calculate E1. Okay, so E1, so here we have to calculate the electric field at point A. So A is this point. Okay, so so first let's calculate the electric field due to the charge Q1 and then Q2. So E1 will be K Q1 R1 square, and R1 is this. Okay, so separation between A and Q1. Again, don't use the sign, okay, for charges. So it will be just 9 times 10 to the power 9 Newton Newton meter square per Coulomb square, and then charge is 50 microcoulomb and 60 centimeter means 60 times 10 to the power minus 2 meter square. So E1 is, I got 1.25 times 10 to the power 6 Newton per coulomb. Similarly, you can calculate E2, K, Q2, R2 square. Okay, 9 times 10 to the power 9 Newton meter square coulomb square, and Q2 here is 50 microcoulomb. Okay, 50. Oh, okay, so microcoulomb, and then the separation is 30. So 30 times 10 to the power minus 2 meter square. So it will be 5 times 10 to the power 6 Newton per coulomb. Now here what we get are the electric field, the magnitude of the electric field. Now we have to determine the direction. Okay, so to understand the direction, okay, so let me, okay. So to understand the direction, again, we can place a positive test charge here at point A. Okay, so if we have a positive test charge at point A, okay, let's see how it moves for individual charges. So here we have Q0. Now Q1 is negative, okay, and Q0 is positive. So let me, okay, so this is our x-axis, this is our y-axis. Okay, okay, so for Q1 it will move in this direction, right? Because Q0 is positive, Q1 is negative, they will attract each other. So the direction of E1 is this one, right? And the direction of E2, because both here Q0 and Q2 are positive, the direction of E2 will be again this one, right? Because they repel each other, right? So because they repel each other, this will be the direction E2. Okay, and similar to the last problem, you can show that this is 30 degree. Okay, now again you see that E2 is only along the y-axis, but E1 is along neither along the x or y, so we have to break it. Okay, similar to the last problem, I mean number 4. So if you break it, so this will be your y component and this will be your x component. So this is E1x and this is E1y. Okay, so E1x will be E1 cosine 30 degree, and E1 is 1.25 times 10 to the power 6 Newton per coulomb cosine 30 degree, and this is equal to 1.10 times 10 to the power 6 Newton per coulomb. And similarly, E1y will be E1 sine 30 degree. Okay, we should have a negative sign because you see the direction of E1y is downward, which is in our convention negative. So it will be negative and the value I got is negative 0.63 times 10 to the power 6 Newton per coulomb. E2x equal to 0 because there is no component along the x-axis, and E2y will be exactly equal to E2, and that is equal to 5 times 10 to the power 6 Newton per coulomb. Okay, so then you have to add the x component together and y component together. Okay, so it will be 1.10 times 10 to the power 6 Newton per Coulomb. Okay, when you add them together. And then similarly, Ey will be E1y plus E2y. So E1y is negative 63 times 10 to the power 6 Newton per Coulomb plus 5 times 10 to the power 6 Newton per Coulomb, and that is equal to 4.4 times 10 to the power 6 Newton per Coulomb. Okay, so E is square root of Ex square plus Ey square, and then this is 1.10 times 10 to the power 6 Newton per Coulomb square, and this is 4.40 times 10 to the power 6 Newton per Coulomb square. Okay, so don't forget the square. And then if you plug these values correctly in your calculator, it should give you 4.5 times 10 to the power 6 Newton per Coulomb. So this is the magnitude. Okay, and then direction will be this: Ey over Ex, and that is equal to, so Ey here is 4.4 times 10 to the power 6 Newton per Coulomb, and Ex is 1.1 times 10 to the power 6 Newton per Coulomb. Okay, and if you plug correctly in your calculator, it should give you 76 degree. Okay, so 76 degree means it is somewhere here. Okay, and this angle is 76 degree, and this is the net electric field. Okay, so again, please go through it, and if you have question, let me know. All right, and this is the last question. Okay, it's very similar to the last problem. So in the last problem, we calculate the electric field here. At this point, we are going to calculate the electric field at point B. Okay, for the same setup, earlier in question 7, we calculated the electric field at point A, now at point B. Okay, so when we calculate at point B, the separation between A and Q2 and A and Q1 was different. One was 30 centimeter, another was 60 centimeter. But in this case, they will have the same separation. Okay, so you see that this is 40 centimeter, and this is also 40 centimeter. Okay, so yeah, so here is the calculate the total electric field at point B, which is equidistant from Q1 and Q2. Okay, so both 40 centimeter. Okay, all right, so the strategy is exactly same as the last problem, but the magnitude and direction will be different because here the point is different. Okay, so let's try. So again, E1 is K Q1 R1 square, and K is our favorite 9 times 10 to the power 9 Newton meter square Coulomb square, and Q1 is 50 microcoulomb, and R1 is 40 centimeter. Okay, 40 times 10 to the power minus 2 meter square. Okay, so the value of E1 is 2.81 times 10 to the power 6 Newton per Coulomb. Okay, E2 is KQ2 R2 square, and then the value, the magnitude of Q2 is the same as Q1. So it is again 50 times 10 to the power minus 6. And R2 is also the same. So it will be 40 times 10 to the power minus 2 meters square. Okay, so you see that it's basically the same magnitude. Okay, it is exactly equal to E1. Okay, now similar to that one, so here our x-axis, here our y-axis, this is point B. Okay, now if I put a positive test charge here, Q0. Okay, so if I put a positive test charge here, okay, at this point, at point B, so due to Q1, because Q0 is positive and Q1 is negative, Q0 will be attracted by the Q1, so it will move in this direction, right? So E1 direction will be this one, and then due to Q2 it will move in this direction, because Q0 and Q2 both are positive. Okay, positive charges repel each other, so Q0 will move in this direction. Okay, so magnitude of E1 and magnitude of E2 are the same, right? Now here, let's say this is theta. Okay, and this is also theta. Okay, you can show that by using that the geometry. Okay, now here you will see, so here one interesting thing is, let me use some other color. So the y component for E2 will be in this direction, and y component of E1 will be in this direction. Okay, so by symmetry this will cancel with this one. Okay, so it tells us there will be no y component. Okay, by symmetry E2y will be cancelled out by E1y, because the magnitude of E1 and E2 are the same, and the angle, you can show this angle and this angle are the same, so there will be no y component. Okay, but there will be x component. I mean, still there will be x component, and x component for both one will be this one. Okay, so this one will be E1x and this one will also be E2x. Okay, so what we have to calculate is basically E1x and E2x. Okay, all right. So then what is, so the net force will be just E1x plus E2x. Okay, now we have to know what is the angle, because E1x will be E1 cosine theta. Okay, E2x will also be E2 cosine theta. Okay, okay, actually the value of E1 cosine theta and E2 cosine theta will be the same, so we can write basically 2E1 cosine theta, but yeah, let's wait. Okay, first we need to understand what is theta here. Okay, so what is cosine theta here? Okay, so cosine theta you can determine from trigonometry. Okay, so this is the triangle, right? And this is 40 centimeter, this is 40 centimeter, and this is 30 centimeter. Okay, so these are the information given, and this is theta. Okay, this theta and our theta will be the same theta. Okay, now what is theta? We have to calculate. Okay, so theta we can determine from uh, from trigonometry, right? So if we know this length, if we know the hypotenuse, so this is opposite, this is hypotenuse, we can easily calculate the adjacent. Okay, so let's calculate the adjacent. What is adjacent? So adjacent, if you use the Pythagorean theorem, you can show that this adjacent, this will be 26 centimeter, and it also showing here 26 centimeter. Okay, so cosine theta from trigonometry, you know that it is adjacent over hypotenuse, right? So it will be 26 centimeter over 40 centimeter, right? And that is equal to 0.65. Okay, so here you see, you basically calculate cosine theta. You don't need to calculate theta, because in this equation you see that you just need the cosine theta. Okay, so E1 is 2.81 times 10 to the power 6 Newton per Coulomb, and then cosine theta is 0.65. Okay, and same thing for E2. The value of E2 is same as E1, so it will be this, and cosine theta is again 0.65. Okay, so if you plug all these values correctly, it should give you 3.66 times 10 to the power 6 Newton per Coulomb. So the net electric field is this, and of course the direction, because both are in this direction, in the positive x-axis, I mean to the right, so the direction will be to the right. Okay, all right, so that's it. So here some of the problems are little bit difficult, so please go through it, and also you can see the solution in the classwork solution. Okay, and yeah, if you have question to understand, I mean if you have a problem understanding this thing, please let me know. Okay, I will be happy to help you. All right, so that's it for this lecture.